with that, I'm very happy to introduce my friend. Probably needs no introduction to many of you. He's kind of an Austin entrepreneurial legend with his exits from Chaotic Moon and Honest Dollar. He's had other also the what's the third exit I'm forgetting? Not just Goldman Sachs and Accenture, but Zynga as well. So he started a quantum computing company several years ago, and I thought he was absolutely out of his mind. And I think I told him that. And then 2 years later, he said, well, you know, what should I do? The market's getting interesting. A lot of people are coming at me. And I'd completely changed course 2 years later and said, don't ever sell. Don't let anyone mess this up. You've got something great going on here. And I don't think he would have anyway, but I like to give myself a little credit for that. And he's built it into one of the most recognizable names in quantum computing. He is a global expert and globally renowned speaker in this topic. Please welcome Hurley, the CEO and founder of StrangeWorks, to the stage.
Wow, you got a little excited there. He totally forgot. Jay did tell me, by the way, not to sell the company 2 years ago. We're gonna see how that works out. Not so sure. I'm not so sure. All right. I'm going to be talking fast. If this goes blank behind me, just everybody be like, it's blank. And then I'll be like, well, look over there. Yeah, so how many of you were here last year when we did a quantum computing talk? I have great news. This is a mostly different talk. For the rest of you, you will be lost completely. We're going to still go over some basics, which will be fun. But this will be a little bit more, last year when Jay had me come by and talk about it, things were still in development, and they are still in development. And we'll talk about that in detail ad nauseum. But things have changed very, very quickly in the past year, just like they have the entire time Jay's been meeting with me about the company. We started in 2018. IBM had few qubits, 15 or so functioning. Then by the end of that year, they had 72. Now we have a 433 qubit machine available from IBM, and soon a 1200 plus qubit machine. So if you think of that ramp over 5 years and you put it in the perspective of 1959 and Jack Kilby creating the integrated circuit, because before that you bought circuits one at a time, and you think about from that point to where we're at now, it's taken a while to get to the iPhones and the supercomputers and all of that. And if I look at the pace for quantum, I think it's going to grossly outstrip that. And when you look at things like AI coming into the play for fundamental research around quantum mechanics and stuff, it's just accelerant on top of accelerant on top of accelerant. So I made an agenda because I know Jay used to work at Dell and he loves these slides. So this is your slide, Jay, if you want to take a picture of it or anything, maybe a selfie, view in the background. So we're going to talk about quantum computing and what it is for everybody who wasn't here last year. We're going to talk about some milestones. When I mean milestones, are like, where are we at in the development? Where is it going? How fast is it going? How concerned, worried, excited, investable should you be? And then we're going to talk about everything around using it. Now, I like slides that don't have a lot of words like this, that are big, but because everybody last time said I had to add more detail, I added a lot more detail, so it's a small font. So good news, details there. Bad news, you won't be able to read it, but I'll read it for you from up here on this screen. And then we're going to go into fact versus fiction. Not a lot of it. I gave a presentation in Tokyo about 1.5 years ago that ended up being the most popular presentation, which was just, that's bullshit, and that's bullshit, and that's true, that's scary, more bullshit, and like that. And so I thought maybe we include the top 3 facts and fictions. So how many of you heard of quantum computing before you came here? How many of you heard about it not on the Austin Forum website? Okay, wow, that's great. This is getting me excited because 5 years ago it was like, how many of you have heard of quantum computing? It was like, nobody. So that's nice. We're in an amazing, amazing situation right now. We are running out of computing power at an enormous pace. When you think about all of the problems facing the world, there's about 56,000 problems in the Brussels Index Cyclopedia, I think it's called, of problems that our species face. And we don't have the compute power to solve them. So when I say that, I talk about things like cancers, talking about exploring the stars, talking about material science, environmental science. We've got, TPUs and GPUs and all this computational complexity, but we have a whole set of problems we're now facing as a species that are what they call intractable. So an intractable problem, basically would fit into any of those categories, be it material science, space, biology, drug discovery, it doesn't matter. And we need to be able to solve these to move ahead as a species. And so with all of these cool tools that we have right now for high performance computing, there's still a bunch of problems that don't work. And so the classic example to give is one that I first saw Michelle Simmons give, who's a professor in Australia, who now has a quantum hardware company doing CMOS silicon hardware. And Michelle's used a traveling salesperson. So you guys have all heard of that, I'm sure, most. So we want to go to 14 cities. I use Jay's laptop. I write a little application to do it and figure out the most optimized path. Takes it a few thousand seconds to do it, right? Jay says, let's not go to 14 cities. Let's go to 22, difference of only 8. That same laptop takes thousands of years. We go to 28 cities, it takes longer than the time of the known universe. Those are kind of a loose framework for an intractable problem. A lot of people argue traveling salesman. That's not my job. I'm neither a computer scientist nor a physicist, so I'll let them have that argument. But that's what I say when I say there's all of these problems that are just outside of our grasp, and it's frightening to me. I think the fact that we're at a computational limit where we're not actually able to accurately give, the right drugs to people that are customized, to give treatments to things, to fix the environment, to create better systems of travel where you could go to Tokyo for lunch instead of it being 18 hours and all that. I think it's a shame. But here's the best analogy I've come up with to explain why we need them, because the 3 questions you'll all put in the chat will be, when will quantum computers get here? Will they break all of the encryption? And will they replace classical computers? It's the same 3 every time. And if you look at Slack for me, I bet somebody, those are probably already in there. But I think of it like travel. I think about being in the United States in the days of the Wild West and taking a wagon and going from New York, from landing on Ellis Island, all the way to San Francisco to pan for gold. And I think about, like, most of your party would probably die, or you might not ever complete the journey. You might have to eat somebody. It could get weird, right? But then we invented the train, and that same trip took 5 to 7 days, right? But no matter how far we go, eventually we reach an ocean. So think of that ocean as computational complexity, and think of the train as all the computers we have now. There's nothing wrong with them. They make our lives easier. They do amazing work. But eventually we reach that ocean. What do we need? Well, we don't need a train. We need a plane. And so maybe think of the relationship with quantum computers and classical computers a little bit more analogous to that. So a little bit more of, it's not a replacement for, it's an amendment to. And remember that these machines are special purpose-built machines. So these machines aren't going to make the cat video on YouTube faster. They're not going to, that's not what they're for. They're not going to do all these things. They are going to do incredible, incredible things. So kind of keep that in mind and think of them as more of a symbiotic relationship. The irony most people don't realize is you can't use a quantum computer without a classical computer, because quantum computers have no memory, right? They have no error correction. They have limited noise control. I mean, there's a lot that we still need to build on these machines. But as I said in the beginning, it's going very, very fast. So to explain this better than the train analogy of how one of these machines works, I have this coin. Now, I did this last time, but I also brought a new trick, which may or may not work as well. This coin has a heads and a tails. And if I flip the coin in the air, it spins. If I set it right here on the counter, I set it heads up, I flip it over, it's tails up. If heads is a 1 and tails is a 0, then that's kind of a classical computer, right? But if I flip it in the air at the top of that spin, is it a 1 or is it a 0? And so if you think about it like a coin toss, at the top of that spin, it's in a quantum superposition of every probability of 1 or 0 until we stop it, we measure it, and collapse it, we don't know what it is. This confuses a lot of people because they think quantum computers, what does it do? What's the output? The output's still a 1 or a 0, right? That doesn't change. It's how we get to the output. So maybe we think of it a little differently. And this is going to be the most disappointing use of cards on stage in history, because I can barely hold them in one hand, let alone do any kind of magic. But I bought a book on that. I tried it on the plane to LA last week. I sent cards flying for like 4 aisles. It did not work. But I have here a suite of 16 cards. And then I have a few additional cards. All right. So obviously there's not 16 cards in a suite. So I've got a Queen of Hearts, a King of Hearts, and an Ace of Hearts added to it. So think about it this way. We are looking for one of those hearts. Every other card in here is a spade, right? So if I pick a card out, say 8, right? I put it back in. I pick out another card. It's a Jack. Okay. That's how classical computers work. If I have 4 bits, I can be in 16 outcomes, but I can only be in one of those registers at a time, right? The beauty of the quantum computer is that I can be in all 16 at the exact same moment in time, meaning I can search a much larger swath of data much faster and much more effectively and go exactly to the King of Hearts that I'm looking for. So maybe that helps put a little more perspective before we dive into how you can use it and all of the fanciness. But again, it's basically a totally new type of computing. You see there, you've got, there's a laser. You've got 4 classical bits. We've got 16 outcomes, but we can only be in one. If we have 4 qubits, you can be in all 16 at the same time. Now, that isn't the only way a quantum computer is more powerful. If we take those 4 and we add 5, we have 25 possible outcomes. But if we take those and we add a 5th qubit, we have 2 to the n the number of qubits, right? So they grow exponentially in the power and in what they can do. It's super, super exciting, but again, not without problems, right? Noise is a lot of problems. Adding a qubit, very easy. Adding a qubit without losing the fidelity of the system to where you can't get an answer out, pretty difficult. Error correction, being worked on, but still pretty difficult. We'll talk about the modalities of machines later, and you'll see there's a bunch of difficulties depending on what modalities you're in. So how does it work on a quantum mechanics level? It's basically a 2-level quantum mechanical system. So it allows for superpositions. As you can see in the map there, you have, instead of that coin, imagine a soccer ball. Straight up is a 1, straight down is a 0. We can rotate it on the X, Y, or Z axis. Or you can do things like a Hadamard gate where you move 2 of them at the same time. And basically measuring superposition gives you a probabilistic outcome of will it be a 1 or a 0? And then we can collapse it. That doesn't mean the machines right now give the same answer every time, nor do you get the same answer across any machines. This is a big, it's not going to work for a lot of people. It's not a problem. That's exactly how computers work when we made them too. So fortunately, this time we already know how to do error correction. We already have some ideas of noise control and how to suppress the noise. So very, very exciting, and it will be a lot better. So where are we today? That first question. When I first started this, it was like 20 years, 10 years, and today. And then it was like 10 years and 7 years. Right now, I would say even the pessimists in my field are down from 7 years to about 5. I think before the end of the decade, it's a pretty common grasp. Google's set their 2029 goal. IBM's cranking away before it. Microsoft's going to try to get back in the game. So I think, 7 years is a really accurate one. I think it's probably before that. Optimist don't think it's 3 years anymore. They think it's, any moment now, right? The irony is you're seeing all of the investment from VCs in quantum now dry up. And so a lot of the quantum companies are not doing as well or having trouble raising or moving or pivoting into other spaces like AI right at the moment where it might hit. And that's just the problem with every startup, which is timing is everything. And so, I feel very lucky that we started kind of right at the right spot, not too fast, not too far ahead, not too far behind. So where are we at in the development of it? Quantum milestones and timing. So great news. I have here a copy of Time magazine, and I am 100% certain that this Time magazine says, Quantum Leap, it's here. Have you guys seen this? Anybody seen this? I'll give away, if anybody wants it, I'll give away the 2 copies I have. So that's amazing. You want to know what the only problem with that is? Can anybody guess what the problem with that is? You can talk. You guys are the quietest audience ever, so you can say something. What do you think the problem with that is? It's kind of true. See, the only problem is in February 17th of 2014, it was also on the cover of Time magazine, and it had arrived. So I'm just like, I'm not saying time is not great at the whole predicting technology thing, but what happened? Yeah, what happened between that one and that one is both tremendous and yet not enough, because we still have a long way to go, as you said. But there's plenty of availability. These are just a few of the companies that we partner with today. And to give you an idea, you've got, let's see, hardware with Atom Computing and AWS and Azure, as well as Blexmo and Deloitte. CQC also hardware, called Quanta Hardware. Blue Cat getting in hardware, Hitachi in hardware, Honeywell in hardware, IBM, obviously, IonQ, obviously, NVIDIA, NEC, IQM, Quandela, QEra, QMatrix, Toshiba. Most of these companies up here are actually hardware companies who have quantum computers that you can use today. So no, they're not perfect. No, it's not here, but there's no reason to wait. Everywhere I go around the world, I ask people about why they aren't doing something with quantum computing. And every time I do, I get the same answer, which is my effect of, like, maybe your first computer was like a DEC or an Apple IIe or something. You're like, like, look at this Apple IIe. It's amazing. You're like, yeah, it doesn't really do a lot of stuff. I'll wait for the iPhone. It's like, why would you do that? There's so much stuff you could be using. And here's the catch, and we'll talk about this in a little more detail later. You cannot take a developer and make them a quantum developer overnight. It is not possible. Trust me, that was one of the original goals of the company. I was like, I'll take all the developers in the open source community and I'll move them all to quantum. And I moved 2 over the last 5 years. So it takes a little bit more work than that, I'm afraid. But if you think about it from a timeline of where we're at, classical to present, we're now probably getting a lot of value if you want to get into quantum with what's called quantum inspired, where you use algorithms inspired by quantum computing on a classical machine. This is what NVIDIA has been doing with QQuanta and a lot of their activities. So really, really important. It's a great place to be, because I think we need a stepping stone to quantum for most enterprises. And that quantum inspired area is really great. We're right here where we've kind of got that down. And now the annealing stuff that's been promised for about 20 years is coming into play. And then somewhere soon, we'll get to the gate model stuff. And we'll talk about these modalities, but basically, you're talking about going from classical doing quantum algorithms to quantum annealing, which some people argue, how quantum is that, to quantum gate computing. This is phenomenal that we're right here at this moment in time at the intersection with artificial intelligence, because I believe these two technologies are symbiotic. You need AI to help discover some of the fundamental things we need to know about quantum mechanics and noise control and all of this, because there's too much for people to do. And AI is already creating algorithms that can't run on a classical infrastructure. So I think these two are symbiotic. And when you get to the point of talking about AGIs or superintelligences, I don't think that you can have one without a quantum underpinning. And so I think, crazy statement, I think there'll be another AI winter, even though I know it seems like we're there. I don't think we're there yet. And primarily because if you look at the cost, right? Most of the people for OpenAI, which is ChatGPT, is the one you all know and love. They don't pay for it, but they're paying millions of dollars in just GPU cost alone. So $10 billion sounds like a lot of money until you do the math, and then you're like, okay, there's a few years runway, just like any other startup. So I think there's a lot of stuff that is yet to happen. And I think part of what will cause that winter will be regulation. And I worry about the regulation coming over into quantum, because people are already worried about the encryption. That other question I mentioned, is it a threat to national security, so on and so forth. So I like to look on the positive things, though. But so let's talk about what you can do with that value for it today. So the typical mentality, like I said, is quantum advantage. We've got to have that. What is quantum advantage? It's a point at where a quantum machine does something a classical computer simply cannot do. Okay. And everybody seems to be waiting on that, partially because of our community, because we've built it as such an important moment that everybody's like, great, get there, and then I'll buy a machine or I'll use it. And we've been ignoring how you can generate value today, get a quality result, speed up your execution, and cut the cost of computation using some of the things we're learning from quantum mechanics on a classical machine. This is super, super valuable, though. What are the milestones of getting to that advantage? Well, questionable whether quantum supremacy has been demonstrated. Google said it. A lot of people said it was a mistake in their lab, that they'd seen the same thing in their labs. This is a big fight. Then people got really upset about the word supremacy, because like white supremacy or something. I don't know how they correlated that, but it was a huge thing for like months. You had to be real careful. You'd be on stage, you'd be like quantum supremacy, and somebody yell the water bottle at you. So we changed that to advantage, aka computational advantage. In the next 2 to 5 years, I think we're going to see the initial quantum advantage. I can't get into too many details, but we have a ton of people using our stuff, and we have 40, 50, 60 partners, and we're already seeing examples of there's a clear advantage. Now, John Preskill is one of the most famous people in the space, did a white paper over a year and a half ago. I want to say it was December 21. And in that white paper, they showed that for machine learning, which is obviously a super hot topic right now, there are already advantages in using a quantum computer. They did about 1,300 experiments over 40 gates on a gate-based machine. And that white paper, if you look for Preskill quantum advantage, I'm sure it's the first thing that pops up. But it's going to still take 5 to 10 years for to get us an enduring quantum advantage. And remember, these machines still have so much to fix. Now, I'm excited. I think you should all run out and work with them today. But what, when we say, why is 5 to 10 years if we're going to get it in 2? Why is it going to take another 8? And part of the reason is just the machines are hard. We'll get to the modalities, but are you trapping an ion with lasers? Are you freezing something down as cold as space? Whatever you do, these environmental variables in the machine are super, super important. So you run into situations where, the rotation of the earth or gamma rays or all kind of stuff can affect them. And that's why when you look at a quantum computer, it's probably as big as this stage I'm on or somewhat similarly sized. And in the middle of it is that chandelier that we saw on the cover of Time. That's not the quantum computer. This little tiny black square right there is the quantum computer. Everything else in there is cryogenics. Everything else in there is theater to bring it down and get it cold enough to put it in there. So very, 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 very likely that we'll get to quantum advantage soon, but that we won't have it sustainable and perfected for quite a while. And I believe you'll see the quantum classical intertwined for another 15 years at least. So what are quantum inspired technologies? Well, there's a ton of them. As I mentioned, NVIDIA has QQuanta, Azure Quantum. I don't know why I'm pointing to that one over there. Azure Quantum has several, and so does AWS. So if you want to use quantum computing today, you can go to any one of these and Strangeworks, and you can access quantum inspired algorithms that you can run on GPUs that you can start looking, playing with, and getting an advantage. The difference being there is that you go here from a lot of simulation or specialized hardware. Okay, so quantum inspired algorithms on special purpose hardware from Hitachi, Fujitsu, Toshiba, everybody, to the actual quantum computing. And that first stage, we said we're going to be annealers. And if you're going to talk about annealers, you have to talk about D-Wave. It's the oldest company in the space. They are pivoting as well. I hope not too far, but they have them. But when you look at the gate-based quantum computers, you have IBM, Quantinuum, IonQ, Rigetti, Xanadu, and QEra is one of almost 60 companies in the gate-based space now. And they're everything from started 2 weeks ago to IQM in Finland to Pascal in France. They're everywhere. And so right now there's enough money in the space, there's enough science in the space, and there's enough kind of gravity, if you will, that I think that next 2 years for breaking through something to get to that next level is going to be super, super important and definitely happen. So, pros and cons to each. I know the type is small, but, major pro for optimization is you can use it today and you can do it. Quantum has this exponential speed up and everything, but, not yet demonstrated business value and unknown when. It's kind of a big one if you're selling product to enterprise, or so I've been told. Cons on the quantum inspired is limited use cases, because when you do quantum inspired, you're taking somebody else's work that they've built an algorithm around, and they've taken that algorithm, and in the case of Toshiba and Hitachi, I'll put it on specialized hardware. They've taken that specialized hardware and made it a whole delivery system for you. So you are somewhat limited. A lot of people would compare it, for this room, like a Mac and a PC, right? You got a gaming PC versus this laptop. Like I can't really expand a lot of stuff on here, but at gaming PC, I can add and chunk all kind of things in there. Think of the gaming high-end PC as the quantum computer. Think of the, very simple, easy kind of pre-used Mac as what quantum inspired is. You're not going to revolutionize science with quantum inspired, you will save your company money, you will get to answers faster, and you will solve some complex problems that you haven't before. So what you need is a quantum flywheel. So this is the one we use at Strangeworks, and you can all take a screenshot of it and do it or whatever. But you basically need to start with defining your strategic business goals, and then you can create some use cases around them, build a proof of concept, create your application on our platform, and then you can iterate and benchmark it, compare it. How much faster is it? I mean, you may have problems where you run on a quantum computer and you say, oh my God, it's infinitely faster, but the quantum computer was $2,600 an hour and I can do it on a GPU and they're like 15 cents, an hour or whatever they are today. So you have to have this flywheel. You have to have some way of pulling this into your enterprise and figuring out how you're going to use it, what you're going to use, and where you're going to take your next steps. Which leads us to what's all of the things you need to know and that we can do with this, which is the most text on any slide. So modalities, but you can take a picture of it or whatever. It's a really good slide. It's got them all. So we talked about quantum annealing. The next one is trapped ions. So IonQ, Honeywell, these are the kind of formats they're using. So they blow up a salt atom, pull electron off, or whichever way they do, and they suspend it with lasers and use microwave pulses in most of these models to adjust that and turn it around. Superconducting qubits, very cool. This is where IBM and several others are playing. Then you've got photonics, like PsiQuantum and others are messing with. Cold and neutral atoms, atom computing, and now in town, inflection/cold quanta. So there's another company you can say you've heard of if you ever get asked that question again. And then silicon spin, which is super interesting. So what they're doing there is using a CMOS architecture, and they're entrapping the quantum part under it, and then it kind of figures it out, and then you still flip a switch. And that is being argued whether it has a lot of potential or not. Here's where I know it has potential. We know how to make that. Like silicon is something we've got down pretty pat. And so I think that to me is the sleeper category as far as hardware modalities and what's going on. I think annealing will go away, so you can just trap through it. I think trapped ions will run into some physics limitations. I think that they're very easy to expand and you can do it at room temperature, but I think they'll get to a point where it's like, okay, if you wanted a 1,000,000 qubit computer, it'd be like the size of half of this room or whatever. I think there's some work that needs to be done on that. Superconducting is absolutely hands down the most promising to me. It's what Google's doing, it's what IBM doing, a lot of smart people working on it. I'm a fan of that. Photonics, super cool, whether it be PsiQuantum or NEC or any of the companies doing that. Haven't seen as many customers using it, but I also know that some of the photonics companies haven't made their machines available to a lot of customers because they're on a path to get 1,000,000 qubits before they really launch in many of these cases. Cold and neutral atoms are super cool. So I'd say kind of superconducting and cold and neutral atoms are kind of my two. I think we'll get to the top. They have a very long decoherence time, meaning that when we start messing around with all those little soccer ball electrons, the machine starts the decohering process. And so you can have a circuit time, the code that you're running, that takes longer than the machine can exist in the space-time. One of the big challenges with the machines right now. But silicon spin, that's my dark horse. I'm really, really interesting. I think it's, it still requires cryogenics. They only have a few entangled, particles at this point. But again, that one, super, super big. So who are the key players in all of these areas? Again, I made these where you could take a shot of it. I know it's small text, but feel free to take a picture. But trapped ions, my three are Quantinuum IonQ and Universal Quantum that I see the most. Superconducting, IBM, Google, Rigetti, Baidu now, Oxford Quantum Circuits and Amazon Bracket. Photonics, Xanadu, Quandela, and PsiQuantum are kind of in the lead position there. And then Intel's Silicon Quantum and quantum motion in that silicon spin that I'm very interested in. And of course, I mentioned Pascal and Cold Quanta and QEra and the cold atoms. So if you want to take a shot at that, that's mainly the hardware players should look at, in my opinion, out of everybody. That changes, in my opinion, like my underwear about once a week. No, I'm just kidding. So like every day, if you ask me, I'll be like, I heard of this new company and saw this proof and they're awesome. And now they're on my list. So this is as of like 4:35 when I sent the slides to Jay, right? Whoops. All right. So algorithms. So that's the hardware. We've got a bunch of modalities there. What about algorithms? Really four combinations. Combinatorial optimization, machine learning, simulation, and cryptography. Those are the four main areas we're seeing it used right now today. What are you simulating? Molecular simulation. If you had a caffeine molecule, which has 150 or 60 whatever components, and you wanted to build a digital twin of that, you did it on a classical machine, you would need memory that would physically be huge and that's so cost prohibitive, you could never do it. But you could do that same digital twinning in a 160 qubit machine. And like I said, we already have up to 433 and in some cases several thousand qubits that are either in testing or coming. So that's a really interesting area because that opens up a whole new world for drug discovery, whole new world for environmental scientists. I'm very big on the simulation of the digital twinning. Machine learning, I mentioned that John Preskill paper, you can get a quantum advantage. There is no doubt. It is probably what we call quantum machine language because it's kind of like Ant-Man. It's like, do you just put that word in front of everything? They do. They do. But I think it's just machine learning. Oh, by the way, we're doing it on a quantum computer, but quantum machine learning is huge, huge area right now of investment. But that top part, optimization, that bottom part, cryptography, that is both the most realistic thing to get value out of right now and the thing that scares everybody the most at the bottom. And so when you look at the timeline of the business impact and all this coming through, like you kind of near term, 3 to 5 years, 5 to 10 years, and long term, your quantum neural networks, they're here. Your annealers are here. Your classifiers, Monte Carlos, your image classifications, your shallow QAOAs are here. All the reinforcement learning, standardizing Monte Carlos, convex optimizers, all of this, that's still seen as quite a ways away because the software development trails behind the hardware development because the hardware development's been done in a vacuum. Because hardware development's been done in a vacuum, no software engineers have access to these machines to play around with. And still today, it's hard. That's part of why we started our company. We try to make all of them available for free as much as possible. But the problem is we need software engineers messing around with these things to give feedback to take some of these algorithm timelines and try to move them closer in, which I think will happen. I think all of these timelines will very, very quickly change. If you look at use cases across industry, there's some big impacts. Optimization, 20 to 50 billion dollars just in finance and portfolio optimization, 10 to 20 in risk management. Logistics optimization, 50 to 100 billion in impact. Aerospace route, 20 to 50 billion. You move over to machine learning, we talked about automotive algorithms. You want a self-driving car, you're going to need a quantum computer to calculate that. Otherwise, when you get the effects of computing the path of those cars are the same as the effects of the electric cars on our grid. Like I'd love for all of you to have an electric car, even though it doesn't help the environment that much. I love mine. But if we all had one and you went home and you plugged it in, we would crash the grid, right? So similar thing. We're going to need those 20 to 30 billion dollars in anti-fraud, anti-money laundering, 50 to 100 in search and ads optimization. And of course, simulation, pharma, 40 billion, aerospace, 10 to 20, chemistry, 20 to 50, energy, 10 to 30, and finance market simulation, 20 to 35 billion. One of the biggest investors in all quantum computers, hedge funds. So wonder why? Because it's going to make lots of money. And then cryptography, of course, 20 to 40 billion in the encryption and decryption and 20 to 40 billion in corporate and government each. I find those, this is from a BCG report and I love them, but I find those numbers suspicious because they're exactly the same. I figured the government number would be even way higher or the corporate number would be lower. But this is kind of what you're seeing people play around with these things today with these machines. These numbers, this impact you're seeing, this is far out. It's years out. It's not that many years out before you start seeing this impact. And back to the first of the talk, we talked about the transistor, and the integrated circuit, and then where we are today. 15 qubits 5 years ago, thousands today, probably 10,000 in, I would say, 2 years' time. Now, will we have 1 million in 5 years? I don't think so. I also think there's a fundamental problem with not having software engineers involved in the process early enough because I don't think there's anybody on the planet that could program a 1 million qubit machine. I think that will have to be done by a machine, which begets more reason that the AI kind of quantum intersection is happening. So If we expand on those use cases, again, feel free to screenshot anything you want. And I'm going to try to make this available for everybody too. But you've got kind of this near term, you look at finance in white, manufacturing in blue, and logistics in purple. You got credit asset scoring, transaction settlements, all those kind of things, chemical product design, vehicle routing, blah, blah, blah. As we get in the midterm, these are all things people will be doing in the next now to 24 months. As you get into 36 months, 48 months, you got robot path optimization in warehouses, fraud detection, portfolio optimization. It'll really be, most of your robo traders will be using quantum to rebalance your portfolio and just not telling you. It'll appear as a charge at the bottom of your statement. It'll say something really creative like super amazing financial advice. Synthetic data generation, algorithmic trading, which is something that has affected all of our lives, is going to go super steroids with quantum. And you get to long term, we've got derivative pricing, stress testing, financial stuff, auto hedging, but then you've also got the cyber risk simulation and credit risk management. And then more importantly down here, autonomous vehicles and robots and fluid dynamics. Those are two areas where these machines are going to drive more acceleration of scientific discovery than anywhere, in my opinion. I'm huge, huge fan of those. But the near-term opportunity, just to remind you, is optimization. It doesn't matter whether you're doing a machine learning or you're trying to do some sort of simulation or optimizing cryptography. This is something you can do today that is very, very valuable. There are so many opportunities to improve processes around the world, be it autonomous vehicles or logistics, be it shipping a package or designing a drug. Optimization is the king of the hill right now. And I think it will be for about 36 months. And in about 36 months, you'll start to see quantum machine learning come in that much as well. Those are going to be your first two big areas for software engineers, in my opinion. So examples of what people are doing, some value today. NEC does all their product planning and optimization now across the multi-product manufacturing plant using a quantum computer. Now they are using their quantum optimization hardware and algorithms for that, and they are using both quantum inspired and quantum, but super cool. Toshiba is doing high frequency trading and fast detection of mispricings being a really big issue in the financial markets. That's, again, work that's being done today. Hitachi is doing insurance underwriting for natural disaster risk. So taking that probabilistic outcome and trying to come up with as many probabilities of how things could go bad or wrong or right, and then feeding that into a model to try to come up with the right pricing for those assets. Super incredibly cool. I mean, it doesn't seem cool. It's like, oh, insurance pricing, they're doing it. But if you look at the weather data that's being taken in, at the historical data that's taken in, at how much they're crunching and how accurate that could potentially be, it's phenomenal. D-Wave, really cool one that people don't talk about enough, is maximizing the reach of television ads with scheduling by optimizing a bunch of different data sets. They also work with a couple of credit card companies, MasterCard's customer appreciation, their whole system with how many points you get and all of that, all run through quantum computers now. They did a big presentation last year and earlier this year that was very cool. So this isn't just for, high-end science. It's going to affect a lot of your lives in a lot of ways. One way people don't talk about, your autocorrect on your text. That will be something, your search on Google. Why is Google investing in a quantum computer? Because search is still the majority of their business. And guess what? Grover's algorithm, when I was showing about that searching that large amount of data, those 16 outcomes at once, they very much would like that for their search business. Fujitsu is doing global supply chain optimization. That is a published paper. I'm pretty sure you can go read about that one. I think you can read about the NEC one as well. Super, super interesting. So we promised some facts and fiction, and then we're going to get into questions, but we have something cool to show you before we do. And although Jay only has one South by badge, I brought 10 copies of Quantum Computing for Babies for questions in the room. We have another thing, though, that Jay asked for that I'll show you in a minute that I did not have. So I'm going to give you my top 3 fictions and top 3 facts. So every time you hear somebody talk about quantum computer, they say it's 1 and 0 and everything in between. And that is not true. It's a 1 or a 0. It's every probability of them, but it doesn't quite work that way. And I can't tell you how many interviews I have where no matter how much I express that, it's like it's a 1 and 0 and everything in between. He said it, and I get quoted. I'm like, and then all the quantum people are like, "What an idiot!" Right? So I was like, "Please help me dispel that. That is not true." Number 2, Huge interest from the Bitcoin community. That's not how math or quantum computers work, but good idea. They're like, what will it do to affect cryptocurrency? It's like, well, it'll break the underlying encryption eventually. So that kind of ruins your whole thing, right? But there's all these people that have been trying to like use it to mine Bitcoin, all this. It's not what it's for. It's not how it works. There's special purpose machines for intractable problems. Mining Bitcoin, not an intractable problem. That's why you can buy a miner on Amazon today. Number 3, teleportation allows you to travel through time. I could go back to when Jay told me not to sell the company. I would be rich. Okay, but seriously, that's not true at all. The only thing I can say is I wish I would have put this video in the slides, but Jay wanted PowerPoint when I was making them earlier. But I'll tell you this, there's how many of you have heard of the Robux conspiracy theory? It's like my favorite. How many of you like conspiracy theories, right? I mean, they're entertainment. That's sad. It's like 9 weirdos in the room. and me. There's a really awesome one. Every time I see this and somebody asks me this, I send them the video. But this guy's theory, which is a little bit of a digression, but it's hilarious, is that the Rubik's Cube has been solved faster and faster since its creation. And Mattel knows this. And they know that soon people will solve the Rubik's Cube in negative time. And wait, that's not the conspiracy, allowing them to travel backwards in time. But wait, that's also not the problem this guy has. It's an amazing video. And so Mattel is planning to travel back in time so they can take all the Rubik's Cubes from there, bring them to the present, and sell them at 100% margin. Also, not this guy's problem. He literally, his next word is like, and that's great for capitalism. Capitalism's awesome. Here is his problem. The additional weight of those Rubik's Cubes will crush the mantle of the earth, causing Yellowstone to erupt and send us all back into the Stone Age. But don't worry, that's why he and a top team of scientists, which he can't name for their protection and because they don't exist, more likely, is working on the Robux Cube, which is a lightweight alternative to the Rubik's Cube. So they're going to wait till the Rubik's Cube solves them. They're going to use a Rubik's Cube to travel back in time with millions of Robux Cubes to re-engineer the design so that when Mattel does this, we don't all die. So if that sounds ridiculous to you, that's what you sound like when you ask me if teleportation lets you travel through time. All right, facts. Number 1 most important fact. Developers are going to face a learning curve. You trust me, I've got some of the smartest developers on the planet, and we were like, we're software guys, we got this. And they were like, what? Like teleportation, there's an error. How do you debug that? You're like, oh, you got to know the physics. Oh, things aren't entangled. How do you fix that? Oh, you got to know the physics. So there were 4 university programs for master's programs when we started. These 4 programs would turn quantum information science students out. Now there's over 50, which is amazing. So you're going to have the talent pool start to increase and stuff. But until then, there's probably 1,000 people or less that remotely matter or should be doing anything with this in the entire world. And that's horrifying to me. So I did the babies book. So I have another book coming out this month. I'll talk about it in a minute. I'm very, very worried about this curve. And don't get me wrong, Microsoft, and I love them and they're a partner. I'm not trying to poke fun at them, but they have these katas that they did for quantum. The only problem is you like instantiate teleportation. It's like, whoops, it broke. You're like, we got to debug it somehow, right? So these higher layers of abstraction don't really exist at the level they need to for quantum computing. Second, entanglement is the most important thing. It is where a lot of the power of the systems come from. It's effectively the idea that we can take 2 particles and entangle them over any distance, and as we make changes to one, they're reflected in the other. That doesn't mean it's the same thing. We call it like I'm with stupid because it's different, but entanglement is super important. If you want to get into quantum computing, learn about the software development and the software environments. I'll answer any questions for you over the course of the rest of the evening about that, and understand how entanglement works. Teleportation's super cool. Superposition and entanglement are the 2 things as a software developer you will run into the most in that. And fact number 3, which is the most important thing, is this is the most exciting time to be alive in the history of the world. This is the first step away from von Neumann architectures, which is the computer architecture we have used for everything forever. This is the first step away from that. And you are sitting right now at a moment in time that you might as well go back and be like, what, a transistor? That's awesome. What'll that do? Or like the internet, I'm Barnes and Noble. I have bookstores on every corner, right? Like this is a moment in history. It is super, super exciting. It's a completely new era in computing that will bring around biological computers, DNA-based computers and storage, and all kind of other things that these computers will help us solve some of the fundamental problems. So if you want to learn more, boom, there's like 50 or 60 of you that won't get books, but fortunately that QR code will take you to where you can buy that book. I'm just kidding. Quantum Computing for Babies sounds like a joke. It wasn't. Chris Ferry was nice enough to let me join him on that project. And he said, it's going to be harder than you think. And I told my wife, hold on my calls. I'm going to get this rum and Coke. I'm going to write this baby's book tonight. And then like 9 months later, I was like, oh my God, the publisher's like, entanglement is too long a word for a baby's book. We like to keep it to 3 to 5 words per page. And I was like, this book is the worst thing. And so it literally, I used to say, this was the worst thing I ever tried to do in quantum computing. It was so much harder than it needed to be. And it turned out great. And it's the most popular book there. So I'm a dumbass. So I thought, why not do this book? That couldn't possibly, I mean, I'd be like, it'll be easier, right? I can use full sentences and words and stuff. Nope. If you've never read a dummies book, which I probably should have done before I signed up to write one, it's like run-on sentence, boom, call out, boom, pow, tip, boom, pow, continuation of thought. And I'm not going to lie, this book was very hard. So I brought this amazing gentleman, Floyd Smith, here, who has written many a dummies book and is currently working on a lot of quantum and AI stuff with me. And I was like, you know, the publisher is like, we've got somebody else who could write this if you're not doing all right. And I'm like, wait, that was an option? Like, I'm not some credit whore. Like, bring that guy on. Put his name first. I don't care. But this book is what we hope to have tonight. But we didn't meet the deadline. So let's call it September 20th or so. That's when you should be getting a book shipped. So thank you very much. We're gonna take Q&A, but before we do, you want to bring up that website for me? Floyd is in California. He would have loved to be here. In fact, he wants to do an event together. He's like, we should go do stuff together. And I definitely want to do that. But we're going to bring up a website here. And don't show them your OnlyFans, man. You should have pulled it up like before. Just switch to the browser tab. Trust me, voice of experience. But there we go. All right. So if you go to chat.strangeworks.com, a lot of people don't know we've been working with AI for the last 5 years too. When we first got our first investment, 2 of the people who wrote the check, one of them said, tell everybody about the AI. And the other one, who I thought was much wiser and smarter, said, don't mention that to a soul. They'll either think you're an idiot, it's a bunch of BS, or you're never going to get there. And I was like, okay, wow. We'll listen to that guy. This is Schrody Cat. Get it? Because we're software engineers, not comedians. So select no knowledge for me there. So we're going to select no knowledge, and we're not going to pick a topic. We're going to, who has a question they want to know about quantum computing? Come on, really? Yes, sir. He said, how do qubits search all the space and come together with the answer so quickly? So we're going to translate that into quantum speak and say, how does Grover's algorithm work? Can you type that in there for me? All right. So there we go. And then he's just going to hit go. And then you're going to witness the power of a $10 billion investment. Because watch, boom, that was OpenAI. Now this is the server running in my closet. So it's going to take it a minute. So we use OpenAI, we use ChatGPT for language translation primarily, and for like context and English structure. This is a LangChain with a small language model that we built with all our quantum knowledge. So if you have questions, you can just go to chat.strangeworks.com and ask this. And then I don't have to answer your email in about a year and a half from now. But it works really well. And here's the best part. So once it answers a question, then you can say, can you provide an example of how it could be applied in real world? Are there limitations? You can pick any one of those you want, but you can dig deeper and it will tell you the things that most people have been asking and lead you down that rabbit hole. And the intention here is that it learns a lot about you. You can click on one of those if you want. It learns a lot about what everybody's asking and what you're asking. And the beautiful part is that the idea here is that we're building another model that will pull all the hardware and software resources you need so that at the end of your conversation, you can just boom, consumption purchase everything you need and work on that project. So put all the algorithms in the right place, and the hardware, you need some quantum, you need a GPU, whatever. It'll symbol all that for you. So feel free to use that. And with that, Jay, we have a few moments. I know you have questions and answers, right? Okay.
All right, first let's give a round of applause to Hurley. I also want to thank all of.
At 4:30, I told you I'm making the slides. It'll be fine.
Yeah, I got the slides after I got here at the library today, but that's okay. So I want to thank all of you for coming. For the first time since the pandemic, we broke 300 in attendance. It is combined in person and online, but over 300 in attendance. So thank you. We really want to reach as many people as possible with these talks because they really are about technology and society. You'll notice Hurley didn't just give you quantum physics 101 or quantum computing 101. He talked about the different application areas where quantum computing is going to make a transformative difference. And that matters in these presentations. And that's why we want we want to spread the word to as many people as possible. We're going to do audience Q&A in a second. But first, I have a couple of questions for Hurley as well. And these are really just meant to summarize because it is a complex topic and to convince you that this is real, that it's not some magic, some Marvel movies, quantum universe kind of stuff, but this is absolutely real. So let's chat about this.
You should have told me about those questions ahead of time.
Well, also, by the way, you're the first one to reserve the word quantumania, aren't you?
Yes.
Yeah, he told me that once, and I said, "Oh, Marvel's going to sue you." He said, "No, but I could sue them."
I said I had this crazy idea that I'd do this conference with somebody in town. It'd be awesome, big quantum track, things would be amazing. Unfortunately, I never see that person, so hasn't happened yet, but we're working on it.
Don't pick on our sponsors. All right, so first, I want to just chat just a little bit about the fact that this is real. Quantum mechanics, on which these quantum systems are based, this is one of the best proven theories in all of physics. There's still plenty we don't know about subatomic particles, about dark energy in the universe and whatnot. But Schrodinger's equation, the Heisenberg uncertainty principle, even things like photoelectric effect and two-slit experiment, we have proven over and over in the lab that at the subatomic level, these things have particle and wave properties, right? Not one or the other, but both. And that relates to this, right? But we can have confidence in our quantum mechanics.
It's the basis of it.
Right. And so another thing that sometimes I've been studying quantum computing lately, and another thing that people would ask me is, what seems so exotically different? But Hurley, as you showed in your examples up there, many of the technologies actually leverage CMOS technologies, pieces of the classical computing ecosystem, right?
Sure. And it's dependent upon the classical computing ecosystem right now. I mean, there are no memories in these machines. There's no such thing. So you usually have a classical computer sitting behind, besides say like a superconducting qubit. You take the data from there. It's usually a little bit of data because you can't do big data stuff. So I like to think of it like this. Don't think of quantum computing as big data. Think of it as big math, right? And that puts your head in the right place. But yeah, they're interdependent. I mean, you need the systems to run the cryogenics. You need classical computers. You need classical computers to get the data and send it to the machine to cool it down. You get it to interpret the answer on the way back out. This will all change very, very quickly. There are a few companies working on memory. There are a lot of companies working on error correction, things like that. So that's what I'm saying. You'll see it take off very fast, but you're never going to get away, not for a long time, from either a classical dependency or just a use case like we were talking about earlier. Like, the GPU cost me 15 cents and this thing costs $2,600. And in this particular problem, maybe it's faster by like 5 or 6 days, but maybe I don't mind waiting and saving $2 million, right? So you're going to see that kind of interplay between them for the foreseeable future.
Yeah, I was actually getting at a different point though, which is in some of those methodologies like trapped ion, they're literally using the same kinds of etching technologies
Oh yeah.
for that. And the key there is you all are already using computers that use subatomic particles. Electrons are flowing in semiconductor materials.
Well,
At this scale, though, you have to manipulate individual qubits.
well, and
That's why
that brings up a really interesting point, which is this all came from a paper in 1980, which basically looked at the computer as a physical system, which was a new way to look at it then, and still for a lot of people today, because everybody talks about digital transition, digital marketing. But if you look down inside of my iPhone and you go all the way down, it's a physical system. There's a little physical piece of electricity being held there by a gate or passed through to get an answer. So this is just kind of, I think, looking at these systems like we should have been looking the whole time. And like you said, you already use a lot of the fundamental technologies that go into building these. You already use them, just a different set, and then some new stuff kind of added on top.
Yeah. So the physics is real. It's using the same kinds of particles that we already manipulate in electricity and classical computing, but it's manipulating at a much smaller level, and it's taking advantage of superposition and entanglement, which means insulating it from vibration, from thermal effects, et cetera, because it's just much more sensitive when you're dealing with that, right? Okay, so I want to make sure that we have time for audience questions. And so with that, I've invited a friend of mine, Art Valentine from IBM, who has been in the audience, looking at your questions, marking the ones he's going to ask, and saving a couple for candidates for the South by badge. Please welcome Art Valentine from IBM.
Come on, Art. Thank you. A lot of great questions. Good talk, Hurley, by the way. When are you going to come back to IBM? Well, I'm sorry. That wasn't a real question. After drinks, after a couple of networking beverages, then we can talk about that, because I already know your response to that. But a lot of really good questions through the chat, and you answered quite a few of them. So maybe you can just go a little bit deeper on a few of these. And Jay, just let me know on time when we got to get to the end here, because there's quite a few questions that are out here. Let's see. Well, you talked a little bit about this one. Is there a quantum corollary to Moore's law?
Oh man, that's a hot topic, because there are 24 physicists I know that would love for that to be named after them. And about 1,000 computer scientists are like, let me tell you how this whole thing's going to work. So you're going to build this computer, and then there's going to be this law of, it could be called Hurley's law. I don't know, but they're not that you could take to the bank, right? And part of the problem with that is, think about Moore's law. Moore's law comes into place at a point where the technology is developed enough that the technologies are all fundamentally the same, right? They're kind of the same modality. We've got transistors, we have these integrated circuits. Now we're putting all these, where we're at with quantum computers, all of those modalities I showed you are like crazy different. Are you trapping something with a laser, or freezing it down, or doing this or doing that? They use different techniques. They have different decoherence times. So for us to get to Moore's law for quantum computing, we're going to need some kind of fallout of we can't have 20 different technologies. We'll have to get down to like 2 or 3 or 4, and then we'll have to have something that we can say, okay, here is a standardized solver and problem that we can test to benchmark them, and then we'll have the data to be like, whoa, it's doubling every month, or whatever it is. But like, we couldn't really realistically measure that today.
Okay. All right. Here's one from Eric Schwartz. You mentioned regulation as a risk to realization of quantum computing. What do you perceive the quantum issues to be that are apt to attract regulation, and related to what do you view on what impact quantum computing will
That is
have?
a great question. Who asked? You read that name though, Eric?
Eric Schwartz.
Is that where are you, Eric? Eric's online?
Eric must be online.
Man, all right. If Eric will send his address to Jay, I'll mail Eric a book. But that's a great question. So I'll try not to get on a soapbox about regulation. I'm not against regulations. All right. But right now, every country in the world is seeing quantum computing as the way that they change their economy, the way their national security is raised to a different level, how they can become a superpower. And so you're seeing a lot of nationalism in quantum computing. right? If you're in France, you're probably using Pascal, Finland, IQM, so on as IBM, US, like there's this weird kind of nationalism thing happening. So with that as an underpinning, think about the regulatory. Every article you read where quantum physicists, and I am just calling it out because I hate this, go to meet with the president, doesn't matter if it's Trump or Biden or whoever, that article, that output from there ends up being like, holy shit, encryption is dead. This is the scariest shit I've ever seen in my life. And at the back of the room, there's always somebody from the Department of Commerce who's like, oh, that's no problem. We got export controls and fix that this afternoon, right? And somebody else who's probably a senior staff member who are the ones who write all the policy who's like, well, we can't have that. We'll just have to write up a bill to say, quantum computing can only be used by Americans. Now, we got hit with the OFAC list before we even started, which we already knew. OFAC list is all the bad actor countries we can't send technology to, and we block them and do what we can on that. Now you're seeing people wanting to regulate the scientific aspect of quantum, people wanting to regulate who can get the technology, who can have access to it. You're seeing people talk about, and this is globally, not just in the US, people talking about how many qubits can we let a normal person has versus a company versus an enterprise. Talking about limiting compute power for people. It's super scary, but most of it comes from encryption. And the fact that there's a thing called Shor's algorithm, which has 5 simple steps, that was created by a guy named Peter Shor in 1994. And when Peter created this algorithm, it was seen as this is, if we had a quantum computer of significant qubits, the way that you could give your public key to me, and I could put it in the quantum computer, and it would give me your private key. And then you have no encryption. And so that is unbelievably scary to every world leader, to every intelligence agency, to everybody. And that's where I see the biggest regulatory threat coming from. Here's the other side of that. There were these big wars we went through. And we used to have a machine that the Germans used called the Enigma machine, but nobody uses that anymore, right? Do you still use 24-bit encryption? No, you don't, right? Threat and remediation are an intertwining dance. That's security. So I think what we're seeing here, and the reason I'm so against regulation limiting this technology, is that if you came up with the, I think, absolutely stupid idea of computers will never really go that fast, and so we'll take it a lot of time and a lot of compute resources to break an encryption to protect secrets, that's just doesn't sound like a great way to protect your secrets. Sounds like we need to rethink all of that. I mean, we're effectively doing what the Romans and the Greeks did. We're just using computers in a lot longer numbers, right? So maybe it's just time that security is revamped. Positive note, entanglement will allow for quantum networks where Jay and I are talking and Stacy tries to read that, and the simple act of trying to see that collapses the whole system, and it's a completely hack-proof network. Bonus, post-quantum cryptography. Quantum computers can be helpful, very useful in creating that. So security is always a double-edged sword, but that's where I see the majority of the regulatory threat coming from. That's where it'll start, right? Especially when I mean, I don't even say half the stuff other people say, like, this thing will cure cancer in 2 years and build a new bomb that would wipe out other planets from here. People are like, Jesus, shut that down. I mean, I'm not trying to get government funding, so I'm not like, boo. But that's the main thing. So, do you work in the government, sir? No, that's the main reason that the regulatory stuff is coming, is to get money. They try to draw interest. They talk about encryption, how scary it is, and how it's going to take it. Sure, you're going to get a little money, but what you're going to get is a lot of regulation.
Okay, great. Another more tech question from Bruce Crawford. Can you expand on what you mean by high connectivity in the cold and the neutral modality?
Yeah, so basically, high connectivity goes across all of it, right? So when you're taking particles, you're not just entangling 2 qubits, you're entangling as many as you can, right? And so every environmental factor can interfere with that, and that's where that decoherence time comes in. So you want high connectivity, you want the entanglement to be solid, you want it to be scalable, right? And you want to be able to take advantage of all of those quantum mechanics when you do those calculations. So we're not there yet, but there's quite a large number of entangled qubits from several manufacturers at a pretty decent fidelity. So it's not 10 years or 5 years or 2 years. And work IBM is doing, for example, is, Jay Gambetta and those guys are doing incredible work in that. Jerry Chow and all them are really pretty far ahead of the game. I'm still never coming to work with them, just so you know. Just thought I'd see that was a setup.
I see that. Okay. All right. I have another question here.
Now I'll work at IBM like next week. I'll be like, oh, whoop.
All right. Another one. Here one from Mark. I guess this is Mark O'Brien. What kind of software partner makes the best strategic sense for the Japanese quantum hardware manufacturers today and 5 years out?
Well, that's StrangeWorks. Duh. So easy. Who planted that question? Yeah, slow pitch. No, software partners who have specialization. There's some great companies in Japan, JIJ. There's one in Germany, Quantagonia. These are optimization experts that have done classical optimization for years. They've also done some quantum inspired and quantum optimization. Those are really good partners because they're going to be able to take the hardware and algorithms that Toshiba and NEC and Hitachi and everybody are putting out and actually deliver them as a solution set to customers. So it's probably a software company that's experienced in like QML or optimization, and probably a software company that has some consultative aspect to it. Because another hard lesson I've learned is I'm like, look, I have 100 billion computers online and all the algorithms. You're like, that's amazing. We'll take one. And you call a week later, you're like, hey, did you log in or use it or do anything? And they're like, what do we do with it? This shit is hard. So somebody with a consultative nature would be pretty important, I would think.
Okay. All right. Here's a question from Juan Cano. What is the environmental cost to support the need and the demand of quantum computing? Will this cost grow linearly or exponentially?
Is this person in the room or not in the room? What? Here, coming up here while I'm answering this and grab this book from me. That's a great question. I'm going to ask everybody to give you a round of applause for that one. There you go, my man. So this is the most exciting part about quantum computing, is that if you look at the work it's doing, it is similar to a supercomputer like the Titan or the Jaguar or whatever, using the fraction of the power. Now, the cooling systems can take a lot of power. Some of the other systems, lasers, different, but those are all things that you can engineer down. And so when you're talking about quantum computing, it is a net gain for the environment as far as computational complexities that we can solve and the energy consumption that we do doing it. So it's super, super cool. And I love that question because it's awesome to be like the computer that could fix the environment, also friendly to the environment. That's a nice, because it is literally the first question you ask when you talk about anything environmental sciences wise, is you're like, right, there's a big black box there with a lot of tubes and stuff going into it. How much power does it take? But you'd be surprised at the amount of power consumption in the other areas, again, which are all part of the solution. So you have to calculate those. But I think you'll see quantum data centers over the next 3 years that are already being built. And if you're familiar with data centers, you get your PEU or PUE or whatever, PEU, right? PUE, right? For the measurement of how much power you're doing, I think you're going to see these things outperform classical data centers, but they're not going to help you get that YouTube video. So we're still going to need those other computers. So I want to be real clear, like not a replacement.
Okay. Question here from Grant Rostick. What stops the flipping coin qubits at the correct searched answer?
So they don't, and we don't know. So I have this prop. So a couple of key points about quantum computing that are in this book that we didn't talk about. And I'm going to use this book to sing. So data can be copied, like when you copy it on your machine, right? Quantum data can't be copied. No cloning theory. So no cloning theory. So if you go further, you can't see what happens in a quantum computer. You can only see the answer it gives. So all of that, much like AI, is a black box of some sorts. It's, there's this kind of still magical process that goes in where we send it in and stuff happens and it comes back. Getting to that solution and depending on the modalities and everything, I don't know that we'll ever see that. Much like AI, it's kind of a black box. We can't copy the data. We can't really see what it's doing. We can set everything going into it and then a process, and we can get that answer back out of it. If it's not the right answer, we can run it again, average them, do other things to get to it. But that's where the error correction is really, really vital.
Okay. All right. You touched on this one a little bit, but I'll ask it again from Ash Barrett. What are predominant programming languages or frameworks that are
Oh,
currently used?
that's actually a great one. Is that person in the room too? Yes, come grab a. Was the other person before in the room? Because they can get a book as well because they asked a question. There you go, sir. And Grant, if you're coming to drinks, Grant, and if Jay convinces me, you can come get your book. No, come get it. Don't be shy. How about what? Oh yeah, you can ask her and she'll be like, sure, 2026. Yeah, but find her. The fact that I'm in Austin is shocked. My wife was like, you're going to be home. That's great. We'll have dinner. I was like, well, so Jay asked me to do this thing. And so she was like, screw it. I'm going with a friend to see Sam Smith. So one of us lost out. Obviously it was her. This is way cooler, right? No. So there are many. So Python, super popular. Usually the programming frameworks. You want to end after this one or one more? Next one's the last question. So pick a good one. That's what he means. A real zinger. You got to end strong, Art. This isn't like an IBM like conference meeting. It's like there's like real people here. They've got emotions and stuff and all that. Anyway, so what you want to pay attention to are the frameworks. So on the StrangeWorks platform, we've embedded all of them, but you can go download any of these by themselves. So IBM has Qiskit, really good. Xanadu has Strawberry Fields, also really good. You've got Google has Circ. Microsoft has Q Sharp. There's a ton of them. The only difference in everything I just said is Q Sharp. So think C Sharp, but they made it a Q, and then they tied it all together with the framework. But outside of that, you're working probably in Python, and you're working through a framework. So the framework will have the library, you know how that works. Obviously, you asked the question. So, but I would say Qiskit is the most popular, not because it's IBM or because I just made fun of them, but what I see coming in across all the machines, across everywhere, is I see lots of Qiskit, some Circ, some Ticket, right? Like which Ticket is another one that's done. And those are like the three I see the most, I think, when I'm out talking to people and they're talking about them. So this is the last question.
All right. Is this one for the okay, yep. Let's see
if they're in the room.
Stella Zhao, are you in the room? Stella.
Are you Stella?
Okay. Perfect. This is a slow pitch for you too, though, by the way. But anyhow, what kind of projects and problems?
Maybe it's back to being in an IBM.
Yes, right. What kind of projects and problems specifically is StrangeWorks specifically tackling today?
It's easy. That's such a simple question for you to win on, but I love it. Lowering barriers. So lowering the technical barrier to entry, so people can use this through applications they already use. We've already integrated Mathematica and MathWorks from MATLAB. We have a whole host that we're integrating now. So you can literally like pull down menu or just be like, hey, I wrote a symbolic gate, make it run. We also lower the barrier by integrating it with OpenAI. So if you go to OpenAI today, you can ask it, hey, can you build a, VQE in Qiskit? And it can give you the code. Then what you immediately should do is say, is that code correct? And he'll be like, nope, whoops, forgot that. But things like that, lowering the barrier to cost. So you can use StrangeWorks for free. We also have a program called Backstage Pass, where if you have a really cool idea and you can't afford to get it to a machine, we will either pay for that or get the partner to give you the machine, because it could be super cool project you're working on. So lowering the technical barriers, lowering the cost barriers. And then the third area is kind of changing the way that we do software development. My kid is 7 years old, and he asked me how to write a Roblox game. And I was like, I have no idea. Is that like a lightweight Rubik's Cube? He was like, no. But every morning, my kid walks in the kitchen and says, hey, Google this, or hey, Google that. And so I said, why don't you ask Google? And then I showed him how to use his iPad to talk to ChatGPT. And so he's been building a game. He has no idea what he's doing at all, right? And he's changed it like 80 times. But that's the future of software development, is machine-assisted development off of you being the creative, having an idea. And so we're doing a lot of stuff to really try to push that forward. So obviously, it's a 25-year plan I have, 5 5-year chunks, 5 1-year chunks, quarterly sprints in between there. When you look at that and you say, okay, what is that future look like? It probably looks like an AGI or an SI that does software development. And I think the whole future of software is going to change. I think in the future, there won't be an app store for Apple. There won't be an app store for Google. You will ask your phone a thing and it will create software to do that in that moment in time. And then it will spin it off to something else and create the agent-based models that just kind of keep spinning off and answering your questions and figuring out what it needs to do it. So lowering the barriers, technical barriers, lowering the cost barriers, lowering the access barriers, and then trying to change, basically the barrier to being a developer. Like so many people are developers right now that shouldn't be, don't get me wrong. They're caught in this weird non-Goldilocks type area because it's like, really, they're not developers. They went to some night school or learned from YouTube or whatever, and they can do stuff, but we all know they're cutting and pasting from GitHub or using GitHub Copilot.